This video is for Chapter 6, the normal distribution. We're going to look at some backwards normal problems. Let's look at number 1. It says an athletic association wants to sponsor a foot race. The average time it takes to run the course is 58.6 minutes. And with standard deviation, 4.3 minutes. If the association decides to include only the top 20% of racers, what should the cutoff time be in the tryout run? Assume the variable is normally distributed. So we know that X is normal with mean 58.6, standard deviation 4.3. So this problem is a little counterintuitive. Normally your top 20% is going to be on the right side of your normal distribution. However, in this case, the top 20% is going to be at the left. The reason for this is because the faster you run the race, the less time you're going to run it in. So the top 20% of runners will be running the race in the shortest 20% of times. So the way we set this up is the probability that X is less than X naught, which is what we're trying to calculate, is equal to 0.20. So our first step is to find our Z naught by looking up the 0.20. So we go to our table and we find the closest thing to 0.20 possible. And notice that that is 0.2005. The next closest would be the 0.1977, but that's not as close. So our Z naught is going to be negative 0.84. So we have Z naught equals negative 0.84. So now we need to unstandardize things. So X is equal to negative 0.84. Multiply that by our standard deviation of 4.3 and add our mean of 58.6. And that gives us 54.988 minutes for the fastest 20% and the cutoff time. All right, let's look at example 2. It says the average life expectancy of a beagle is 13.3 years with standard deviation 0.4 years. Assuming that the life expectancy follows a normal distribution, the beagles with the highest 25% of life expectancies live how many years? So again, our distribution is a normal distribution. This time the mean is 13.3 years with standard deviation 0.4 years. So drawing our normal curve, the beagles with the highest 25% of life expectancies, they're going to be over on the right because more years is going to be to the right, so we have 0.25. So we're actually going to set things up with the probability to the left, which is the 0.75. So remember, these add to 100, so this is just 1 minus 0.25 gives us the 0.75. So we're setting out the probability as the probability that, so we're going to set up the probability such that the probability that X is less than X naught, here's our X naught, is equal to 0.75. So now I need to look up 0.75 on my table and find the Z naught value. So 0.75, this is the closest right here, 0.7486. It's a little closer than the 0.7517. So my Z value is 0.67. So Z naught equals 0.67. So now I unstandardize. X is equal to 0.67 times my standard deviation plus my mean, and that gives me 13.568 years. All right, let's look at example 3. It says the average life expectancy of a beagle is 13.3 years, with standard deviation 0.4 years. Assuming that the life expectancies follow a normal distribution, what is the 25th percentile for the life expectancy of beagles? So again, our distribution X is normally distributed with mean 13.3, standard deviation 0.4. We're trying to find the 25th percentile. Percentiles we can always set up with the probability to the left. So we have the probability that X is less than X naught is equal to 0.25. So I first need to find my Z naught value. So we look for 0.25, and the closest value to that is the 0.2514. 0.2483 is a little further away. So negative 0.67 is my Z naught. So again, we unstandardize, so we get negative 0.67 times our standard deviation plus the mean. And that gives us 13.032 years.